bit. I think I've just got a few more slides on this. I just wanted to do all of this XPS talk in one go. So here's another look of a full photoelectron spectrum in more detail. And let's dissect this, okay? So here you can see at zero binding energy, these are the electrons that are furthest away from the nucleus. So that VB right there stands for valence band. And now what we're also looking at here, you can see this is titanium oxide. So we're actually looking at a molecule, okay? You can see we're also seeing what the incident radiation was. 730 electron volt would be the incident radiation. So that means the highest energy we could go out to would be just under 730 electron volt. Because with the binding energy of 730 electron volt and an incident radiation of 730 electron volt, we wouldn't have any kinetic energy, right? So everything down here has the highest kinetic energy, right? Consequently, the smallest binding energy. And so now as we scan across, we can see various features corresponding to titanium and oxygen, right? So here is the oxygen 2s, the titanium 3p, the titanium 3s. So here you can see in this region, we see the Auger peaks, okay? And sometimes the Auger peaks can be really well defined, such as this oxygen or titanium, but sometimes they're not so well defined. Actually, excuse me, the oxygen is the only one of these Auger peaks that's really well defined. This carbon 1s right here, this is an XPS peak, okay? So carbon 1s, if you recall, always occurs at about 285. So why would there be carbon in this sample? And the answer is because when you put your sample on the manipulator stage, so right, this is our, I'll just call it the sample stage, right? And here is our analyte, okay? Every now and again, the XPS technique can sample some of the elements on the sample stage if you haven't like manipulated it perfectly, okay? So XPS, as we said, is really, really sensitive. It could also be carbon contamination from someone's fingers, right? So this is a really, really sensitive technique. So here we can see spin orbit splitting from the titanium 2p 3/2 and the titanium 2p 1/2. And just, taking a quick scan at my periodic table right here, we can see that then titanium in the 4+ oxidation state, right? Remember, so this is titanium 4+. So you can see that gives spin orbit splitting in that core level, okay? And so then here you can see we've got the oxygen 1s. So now what I also want to point out is the background shape right here, okay? So the baseline or the background in XPS is quite terrible. And the reason for that is because there's also a lot of stray electrons, secondary electrons, or even tertiary electrons that can also make it to the detector. And those electrons are typically not well defined. They're not coming from quantized levels. And so that gives a lot of background noise, okay? So that's just a really noisy background. And so that's why the process of deconvolution in XPS is really important, because these baselines in XPS are always quite terrible. So let's get a look at chemical shift and oxidation states, okay? So if we were to look at the XP spectra of, let's say, silicone, okay? So you can see it's noted right here. Here is its binding energy, okay? And so this is looking at some of the valence levels. So the valence levels, as you might imagine, are more sensitive to chemical environment. All the same, the core levels are also sensitive to chemical environment. But the reason why I know that this is core levels is because of the really low binding energy that's down here, right? Just a couple of EV. Okay, so here you can see is just silicon. Okay. But now what happens as silicon goes through these increasing oxidation states? So for example, a silicon bonded to one fluorine, right? That's an Si plus. And a silicon bonded to two fluorines is an Si2 plus. And then an Si3 plus and an Si4 plus. Okay. Well, so now when you think about it, you're trying to remove an electron from something that's now positively charged, right? So that's going to be harder to remove that electron. And we can see that with all of these various peaks, okay? That they're shifting to higher binding energies as the oxidation state increases, okay? So that's what we've got right here. Generally an increase in oxidation state causing an increase in binding energy. And that's a wonderful diagnostic, again, of what kind of molecules we might have in our spectra. As you can also see, these peak shapes are not great. So once again, the process of deconvolution, as you've seen in the Spec 1 assignment, is really important in XPS. Okay. So now the last thing I'll talk about is looking at a full-on organic molecule in XPS. This can be done. So this is a look at, oh, I forgot to write it down here. I guess this would be some type of polymer. I'm just going to say polymer. Okay. And so you can see it's got various types of oxygens as well as various types of carbons. And so now, again, if we look at this 285 region where carbon always appears, you can now see it's quite dynamic. For example, the carbon-carbon bond shows up around 284.6 eV. And right here you can see that's corresponding to the carbon-carbon bond in this ring. But now you can see that there is a carbon-oxygen bond from the ether, right, that shows up over here. And similarly, this neighboring carbon molecule is even affected. Even 2 positions over from the oxygen, it appears shifted relative to the carbon-carbon bond. So really sensitive to chemical environment. And you can see the carbonyl region right here, also the carbon XPS energy, the binding energy, shows up over here as well. Okay. And then similarly, if you look at the oxygen 1s, so these are both the same, molecule. It's just focusing on the different region. Right, so oxygen always appears around 532. So I'm going to write that down. Oxygen is always around 532 electron volt. Carbon is always around 285 electron volt, for the carbon 1s or the oxygen 1s. And so now, as you can see, there's 2 different types of oxygen in here. Okay. And those have to be deconvoluted, right? There's the ether oxygen and there's the carbonyl oxygen. And so the diagnostic we use in XPS, again, is recognizing that when I'm talking about triplets or singlets, I only expect 1 peak. But if I see multiple peaks in my XPS, and particularly multiple peaks right on top of each other, that's telling me I have a different chemical environment. That's telling me I have more than 1 kind of oxygen or carbon, for example. However, if I see multiple peaks that are really well split, like these atoms right here for copper, silver, and gold, okay? And particularly seeing these peaks in this ratio, right? Where you can see that the high J value is always slightly higher than the low J value. That's a diagnostic that tells me I'm looking at a doublet state, because those doublet states are typically separated enough that the peaks aren't right on top of each other, okay? So all of these are good diagnostics for XPS. And then the final thing I'll say is, if you were looking at this XPS spectra, and suppose you didn't know this was the organic molecule you were looking at, you would have a really, really hard time assigning all of these different functional groups. So typically, people also use FTIR in tandem with XPS for total analysis. So you see this quite often in literature where someone has taken the XPS of their new and interesting molecule they're trying to synthesize, and they've also done FTIR. The FTIR tells them, you know, what functional groups are present. And then from that, using the FTIR spectra, you can use the XPS spectra to confirm those results. And that's what I would call the spectroscopic kill, when you can use two different techniques that help you identify your molecule. That is a for sure way to characterize everything you want to know about your molecule. Okay, folks, that's all I'm going to say about XPS. The next 2 or 3 lectures or so will be on techniques in UV-Vis spectroscopy. See you in the next video.